Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video number 5. And we're going to finish up counting or enumeration in this video. Before we get started, let's look at the review from last time. I also want to point out that our classical definition of probability, using a discrete finite sample space S, is given here. And we have to count the number of outcomes in the event A and the number of outcomes in the event S, and that is our motivation for learning how to enumerate or count in complex situations. We're using the multiplication principle. The number of outcomes in one experiment times the number of outcomes in another, etc., will tell you the overall number of outcomes. And we learned last time how to do a proof by induction, and mathematical induction requires 3 steps, and I've listed them out here. I would encourage you to know those. I always give a proof on a test that uses induction, so you'll definitely want to be familiar. And last time we talked about ordered without replacement, and we said that if we want to reorder n distinct items, there are n factorial ways to do that. n minus 1, n minus 2, ... times 2 times 1 ways. Now, when we want to select r at a time from n distinct items, then we ended up with this expression, n factorial divided by n minus r factorial. I also want to remind you that 0 factorial is defined as 1. Not 0, but 1. Otherwise, we'd be dividing by 0, and that's not possible. I've also provided this nice table with the 4 basic situations that we covered: ordered, unordered, with and without replacement. Now this section, again, last time we covered what's grayed out. This time we're going to cover ordered with replacement and unordered, both with and without replacement. Without replacement also will cover the binomial theorem and some properties of combinations that are handy to know. So let's talk about ordered with replacement. So many times we're going to do a sample, and then as we choose something, we'll put it back in to the bin, so to speak, so that we can choose it again. If we have n distinct or different items and we choose r of them at a time without replacement, then the first, we can think of it as multiple selection steps. So the first one, our number of choices is going to be n. Since we've chosen one and put it back in, for the second draw, there's still going to be n. And for the third draw, there's still n, because again, we replace it. And we keep doing that until we get to the rth draw. Okay. And so this is n raised to the rth power. And with replacement, notice that it is possible to have r exceed n. Now, we can't do it all at once, of course, because we can only choose a maximum of n items. But if we're doing it as an individual draw, which we can always think of it as, then we can end up with more than n of these selections. Now, let's do an example or two. How many 5-digit zip codes are possible if no digit is repeated? Well, this is similar to, or this is sampling without replacement, because we can't repeat the digit. So we can use NPR. Now the number of digits is 10, because we have to include 0, 1, up to 9. So this is 10P, and we got 5 digits in a zip code. And so if you recall, this is going to be 10 factorial over 10 minus 5 factorial, or we can write it out as 10 times 9 times 8 times 7 times 6, which will give us 30,240 different possible zip codes. Now, what if we can repeat the digits? Well, in that case, we're going to have n to the r, because we're replacing them. And so this is going to be 10 to the 5th, which could be written, if you want to think of it this way, the first, second, third, fourth, and fifth 10 each. So you can either use the formula or you can write it out like I did just here. And this, in any case, you're getting the same answer, which is 100,000. So almost or more than 3 times the number of zip codes allowed under non-repeating decimals or digits. So let's talk about unordered without replacement. So we're going to derive this expression, and in order to do that, we're going to say let C denote the number of unordered subsets of size R that are selected from n distinct items. Now we're going to take just one of these unordered subsets, so we're just taking one of the C unordered subsets, and it has R items in it. And we're going to count the number of possible ordered permutations, and of course that's going to be R factorial. There are C of these unordered subsets or unique subsets, and then so there's going to be C times R factorial total permutations. That means that using our formula, we have that NPR has to equal C times R factorial. Now we can solve for C by dividing both sides by R factorial, and we get C is equal to NPR divided by R factorial, and then we can substitute in for NPR, and we end up with this expression here, which is n factorial over R factorial, and over n minus R factorial. This is the total number of unordered subsets of R items chosen from n distinct items. And we call this a combination. We want unique, combinations are unique. In other words, there's no repeated values in a combination. So here we don't care about the order, and I'll give you an example in just a minute. We also can say n choose R. That's how we can say this without saying a combination or using this notation if we want. All right. Let's say that we want to randomly select a jury that consists of 2 women and 3 men out of a group of 5 women and 7 men. So how many ways can we do this? Well, we're going to use the multiplication rule. We're going to have to multiply the number of ways that we can choose women and times the number of ways we can choose men. So if we have Mary and Jane as women, we don't care if we choose Mary first or Jane first. If both of them are selected, then we have Mary and Jane, and again, we don't care the order. So this is a perfect example of where we have a combination and it's without replacement. You can't choose Mary to take up 2 spots on the jury. She can only take up 1. All right. So we have 5 women and we're choosing 2. We have 7 men and we're choosing 3. And so I'm going to write out this using the definition, 5 factorial over 2 factorial, and 5 minus 2 is 3 factorial. Then I have 7 choose 3, so 7 factorial, 3 factorial, 4 factorial. Notice that the bottom digits have to add up to the top digit. All right, now I'm going to use a trick or technique, but I call it a trick, to make this calculation as easy as possible. Obviously, you could use your calculator and plug these values in and multiply and you get the answer. But if you don't have your calculator, then this will help you understand what's happening. So I'm going to look at the denominator here, and I see that I have a 3 factorial, that's the largest. So I'm going to write 5 factorial as 5 times 4 times 3 factorial. And then I have 2 factorial times 3 factorial. The 3 factorials will now cancel. I'm going to do the same thing with this fraction. 4 factorial is the largest on the bottom. So I'm going to write 7 times 6 times 5 times 4 factorial. Cancel out the 4 factorial. And then I look at the 2 factorial, and that's 2 times 1, so that's 2. And then I have 5 times 4. And then here I look and I see that I have a 3 factorial left, and that's 3 times 2 times 1, which is 6. And then I have 7 times 6 times 5, and so I can cancel out a 6 here. I can divide 2 into 4, and I get 10 times 35, which is equal to 350. All right. So there's 350 different ways, unique combinations of a jury with 2 women and 3 men selected from 5 women and 7 men. Seems like a lot. Now, what if Steve and Harry are 2 of the men and we can select one, either Steve or Harry, but not both of them? Now, how many ways can we select this jury? Well, for the women, it doesn't matter. Nothing's changed. We haven't set any additional restrictions. We've got 5 choose 2, and that's equal to 10. We calculated that up here. This value, this fraction here, turned out to be 10. But for the men, we have 3 scenarios. So the first is we choose Steve. That means we cannot choose Harry. And the ways we can choose Steve, there's one way we can choose Steve. And then there's 7 total men, so we've chosen 1, that leaves 6. And then we've eliminated 1, that leaves 5. So we have 5 choose 2 to get the other 2 men. And this is 1 times 10, which is 10. Likewise, we could choose Harry, and then we could not choose Steve. So again, there's 1 times 5 choose 2, which is 10 ways. And finally, we could choose neither. So again, we're eliminating 2 people, so we're left with 5, but now we have 3 people that we need to choose from the 5. And if you work this out, you'll see that that also becomes 10. So there's 30 different ways to choose the men, 10 different ways to choose the women, so 10 times 30 is now 300, and so we have lost 50 ways that we could choose this jury just by making these restrictions. Now let's look at the binomial theorem. The reason we're looking at this is because the coefficients are combinations, okay? And we call them binomial coefficients. And so we have to look at the pattern. So we have a plus b raised to the r. And so r goes from 0 to n. And then we have n choose r. And then we have b here raised to the r. And a, which is the first one, raised to the n minus r. Again, the exponents here add up to n. So interesting. Now let's do it with p plus q, where p is less than 1 and positive, and q is less than 1, and p plus q equals 1. So we want p plus q raised to the r. So we plug into the formula. It's still r equals 0 to the n choose r, but now instead of b we have q raised to the r, and instead of a we have p raised to the n minus r. And so now we have an expression for 1, because p plus q we said is equal to 1. So that's 1 raised to any power, r, is 1. So we have an expansion, a binomial expansion for the number 1. So here are some nice properties for you to know. That n choose r is the same as n choose n minus r. So n choose r, I'll rewrite this with its definition, n factorial over r factorial over n minus r factorial. And then I rearranged the bottom, because I've worked this out before. I know where I'm going. Okay. N factorial. And now, in order to get this as a combination, I need to write this as the top minus what's on the left. So if I take n minus r, guess what I get? I get r factorial. So I can rewrite this as n factorial over n minus r factorial, n minus r quantity factorial, and that is n choose n minus r. So we're done. Pascal's identity is very handy to know. I would certainly write this down on my formula sheet, and the proof is straightforward, so I'll let you work that out on your own. Now, here's some really important properties to know about combinations. If n choose 0, there is exactly one way to choose nothing out of n, or no items out of n. And that's by definition. So we have n factorial over 0 factorial, n minus 0 factorial. So n minus 0 is n factorial. So we have n factorial over n factorial. And this is 1, not 0. 0 factorial is 1, so we have 1. And likewise, you could do the same with n choose n choose 1, and n choose n minus 1. These two over here give you n ways. These here give you one way. So handy to know. Now let's talk about a distinguishable permutation. The reason we're going to talk about this is so that we can talk about unordered without replacement. And unordered with replacement. But a distinguishable permutation. So each of the NCR permutations of n objects, we could think of them as R of one type and n minus R of the other. Okay? So let's say that we had, instead of distinct objects, that we have n objects R of one type, n minus R of the other. Now let's expand that to what we call a multinomial coefficient, and it's written like a combination, but it's not exactly the same as far as the definition. So what we do here is we just take what's on the top as a factorial, and then instead of doing any subtracting, we'll just multiply the factorials of each of the n1, n2, etc. And this is the number of ways to permute n objects where n1 are similar, n2 are similar, and nk are similar to each other. But those n1 groups are different than n2, those objects, and they're different from each of the other categories of objects. Also, we have to have the sum of these categories add up to n. So let's do an example here. How many ways can we permute the letters in the word probability where we are looking at unique things? So first thing is to count the number of letters. There's 11. And then we count how many of each individual letter. There's one P. There's one R. There is one O. There is two B's. There is one A. There are two I's. There is an L, one T, and one Y. And if I add these up, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I can write this as 11 factorial over 1 factorial, 1 factorial, 1 factorial, 2 factorial, 1 factorial, 2 factorial, 1 factorial, 1 factorial, and 1 factorial. Well, 1 factorial is just 1, and 2 factorial is actually 2. So I end up with 11 factorial over 4, and that gives me 9,979,200 different ways. It's quite a bit of ordering those. Now, the last case is unordered with replacement, and this does not occur very often, and here in statistics at least. So here is the formula. So let's derive it using an example. We're going to roll 10 six-sided fair die. So there are n equals 6 distinct outcomes we can get for each of the die. And we're basically repeating that 10 times. So there's 10 permutations or subsets of this. How many possible unordered subsets or outcomes are there? So we're going to list out R zeros and separate them or partition them into n minus 1 into n categories using n minus 1 vertical bars. So here's an example. So I have a 0 and then a bar, and this is like I've got 1, 1 from the roll of the dice. The second space is for 2s, and I don't have any because there's no 0 in there. And then the third space will be for the 3s, and I'll have 3 of those. And then I put a bar. And then I have 2 4s that were rolled. And then I have 1 5 that was rolled. And then I have 3 6s that were rolled. Okay. So this gives us the a combination, all right, of the outcomes of these 10 6-sided fair die. Now, if we think about these as a distinguishable permutation of R zeros and n minus 1 bars, so each distinguishable permutation is equivalent to an unordered sample. Okay, and the number of distinguishable permutations, hence the number of unordered samples of size R that can be selected of in objects when sampling with replacement, is n minus 1 plus R, choose R. There are n minus 1 plus R objects here. Okay, and so this becomes, using our formula, n minus 1 plus R factorial over R factorial, and then n minus 1 plus R minus R factorial, which gives us n minus 1 plus R factorial on the top, R factorial, and n minus 1 factorial on the bottom. For our example, again, n is 6, so I have 6 minus 1 plus R, which is 10 factorial, and then we have R factorial, which is 10 factorial, and 5 factorial is n minus 1. So 15 factorial divided by 10 factorial, 5 factorial, and this gives us 3,003 different ways, or different unordered subsets without replacement, okay, or with replacement. So please don't forget to scan your lecture notes by midnight tonight. Please make them neat so that you can go back and use them to study or perform homework or test. And if you have questions, by all means, please come to my virtual office hours. If you can't do that, email me. I am happy to help you, want to help you, and so please keep thinking probability theory. Until next time.